Hi, I'm Gaëtan, and I'm presenting our work, Scanner Neural Network for Onboard Semantic Segmentation of Satellite Images. This work was prepared at INRIA under the supervision of Florent Lafarge and funded by IRT Saint-Exupéry. Semantic segmentation is a computer vision task where we assign a label to each individual pixel of an image. This task is usually performed using large convolutional neural networks such as UNet. However, it would be interesting to perform this task directly on board. This would allow us, by only downloading the interesting pixels of images, to save bandwidth, save storage space, and save time. Most Earth observation satellites actually feature push-broom sensors. These sensors acquire the images line by line, which can create large images when we let the acquisition run for a long time. Using a classical CNN inference would incur a high latency, a high memory usage, and a high storage space usage. It would be interesting to design an architecture that can process the images as they are acquired, line by line. We will do this using recurrent neural networks. These networks apply a set of weights multiple times over an input. They feature an internal state that can keep important information. Some people have already used recurrent neural networks, such as the convolutional LSTM, for analysis of multiple images in a row, such as for video. They do this by replacing the linear operations with 2D convolutions. These networks have interesting properties. They have a very low memory usage. They can capture long-range dependencies thanks to the internal state. And they have a very low latency because the output is generated at the same time as the input is ingested. All of this makes recurrent neural networks interesting for our usage. We base our architecture on the conv-LSTM. We replace the 2D convolutions with 1D convolutions. We only use 2 layers. We don't have any pooling and no peeping in LSTM. On the right, you can see the equations of the LSTM. We notice that by concatenating the inputs and concatenating the weights, we can implement this very efficiently using a single convolution operation. You can see our network on the bottom left. To evaluate our network, we perform a cloud segmentation experiment on the 38 cloud dataset. We compare it to our previous work, which was compact versions of UNet and the FCN network. For metrics, we focus on the accuracy, the memory usage, and the latency of our network. Here are some quantitative and qualitative results. The main takeaways are that the quantitative results are similar between the small version of ScannerNet and CFCN, and between the large version of ScannerNet and CUNet++. However, the qualitative results of ScannerNet look more refined than the ones of CUNet++. This is because we perform all processing at the original resolution of the image. So, does this mean that we actually only need a single line to perform semantic segmentation? Well, not quite, because we also run a baseline experiment with a simple 1D convolutional neural network without recurrency. What we see in the first line of the table is that this network does not perform as well as ScannerNet. Next, we evaluate the memory footprint of our network. We find that ScannerNet only requires about 100 kilobytes of memory for its forward pass, which is really not a lot. When comparing to CFCN and CUNet++ again, we see that ScannerNet offers the same level of accuracy at a much lower memory usage. So even though CFCN and CUNet++ were already pretty efficient, it is possible to create a more efficient network. For latency testing, we define the latency as the delay between the start of the inference and the output of the first pixel of the segmentation map. This is only one line for ScannerNet, and it is the whole image for CUNet and CFCN. We evaluate the latency on the Jetson Nano, which is a small computer consuming only 15 watts. We use both the CPU and the GPU for testing. What we see is that ScannerNet offers a much lower latency than our previous networks. It can actually be reduced by a factor of 2 at minimum and by 6 at maximum. Thus, we achieve a very low latency. So to sum up our contribution, we have created a new architecture for semantic segmentation. This architecture can be very useful for push-broom sensors and memory-constrained environments. It allows us to reach a very low latency and it makes it ideal for on-the-fly processing. It is also a proof that we can use 1D convolutions for semantic segmentation. Thank you for listening.